right, hello everyone. So we'll start slowly. So so the goal is to construct the elliptic. We've been talking about elliptic stable envelope for a very long time, so maybe it's time we construct it. So we'll do it in a slightly simplified situation. So if I think you understand the construction in this situation, then you understand the construction in general. So the setup would be the following. So let X be an algebraic simplicity variety. With an action with torus A. So this acts by simplexing transformation. This preserves the symplectic form. And then, but then it fits into a bigger group of transformations. So there's a bigger torus, so there's a larger torus. Torus T that scales the symplectic form with some character. And that character we will denote H bar. So this H bar is, this is in fact when we construct the quantum group, this is the deformation. This is the deformation parameter. So in other words, there's an exact sequence if you want. So then that would be saying that there's a torus T, and then there's a subtorus A, and then there's this character H bar, which goes to C star and goes to that. And then we will make, so we would like, so in general, this could be an non-abelian group of well, let's not worry about that. And another simplifying assumption we would like to make, again, if you understand the construction in this case, you construct this extraction. Let's assume, so for simplicity, assume that the fixed locus is just finite number of points. So Fi, fixed point, these are fixed points. So in other words, dimension, i.e. dimension of the fixed locus is 0. So it means in general, so instead of Lagrangian, instead of constructing Lagrangian, in general, we need a correspondence of Lagrangian here. We just need a bunch of Lagrangians. This zero dimensional is just a bunch of things. So maybe to have a picture in front of R, so there's maybe this is X, and then the different, more around. This is X. Then there's different fixed points, so maybe there's a fixed point F1, and so there's a tracking manifold of F1. And some of these trajectories have hit a different point, 2, and so then there's a tracking manifold of 2. There's a nearby tracking trajectory that goes to F1. Maybe this is not the best example of my drawing. And then similarly, there's maybe this hits another point. Let's call it 3. So similar story. Something like that. And so then for each one of these fixed points, we would like its elliptic stable envelope, and what would be should be elliptic stable envelope of each fixed point. That should be so step of each fi. What should that be? That should be like an elliptic homology class. That is to say, it should be a section of some line bundle that called, since the stable envelope, but called that line bundle curly S. And where would that be on? So if we now look at the what's elliptic? So then this is X, and then there's elliptic T maybe correct elliptic homology of X. So what would it look like? And so then this will have for every fixed point, it will have a kind of a copy of elliptic homology of a point. So this would look something like that, something like this, something like. I'll let the moment hit it. In some way like that. And they all sit. So these are all these are all copies. And then there's also some thickness. Some other fluff. So don't worry about the fluff yet. So, but this is if you're looking for components of maximum dimension, they correspond to fixed points, and that's it. They're all copies of elliptic homology point. And so, which we can further map, to just further maps to elliptic homology of this T of A of a point where this coordinates kind of this is where the parameter H kind of lives. This has the coordinate. This torus has the coordinate H. So then the fibers over that H bar are copies of, so this would be, so fibers over that are copies of elliptic homology, of A correct elliptic homology. And so so this is the line bundle S. And so what we would like about this line bundle? So we would like it to have, what would it look like? We would like to fix, so we want to fix the degree. We will fix its degree in the variables, or rather, the degree of its restriction, the degree of its restriction points in the variable. A. So we talked at length about degrees of line bundles on the Billion variety last time. We decided that this is like a quadratic form, and we will review that one more time. And so what's the degree that we want to, what's the degree that we want to fix here? So so this is, suppose we have a fixed point, and so this is my fixed point F. And then I have some attracting directions, some repelling directions. Let's say attracting directions. These are attract, and maybe they have torus weights Wi. These are the attracting directions. And then there's repelling directions, which we'll maybe draw some different color, this color. F. And so since this is my manifold symplectic, there is a duality between attracting and repelling directions. And so this is for every attracting direction, there's a repelling direction with the weight which is 1 over h bar Wi. So if we denote it, so this is, you should remember that the symplectic form is something in the dual of the space. So it's like the weights of the two vectors. The weight of the bivector, which is this times that, should be 1 over h bar, not h bar. So this is, and so these are repelling. And so then if we look at the attracting manifold of F and restrict it back to this fixed point, what would be this? What would be the class of that elliptic motion? This is the zero locus of a vector bundle whose weights are this. So this is like, so in kind of conventional terms, this is a product of theta functions of, well, theta of, I'll write it here. So theta is symmetric function, so it means theta of x is minus theta of x inverse. So this is, so it means the theta in a somewhere, the line bundle theta is symmetric with respect to reflection in the elliptic curve, but the section changes sign, but somehow maybe not so important. So maybe I'll write a section is a section of which line bundle? It's a section of line bundle which is a product of the same, is a section of the same line bundle as a product of theta function of h bar Wi. Oh, let me just write it in exact equality. This is plus minus product of theta h bar Wi. And so in the variable a, so these are the wi's are characters. So these are weights. Weights of my torus A. And so this in particular, this Wi is my variable AI raised to some power, maybe called mu. And so this has degree. So this is by the formula we computed last time. This has degree. Degree, which is just the summation of all those mu i's squared. So this is in S2 of characters. So in the variables. So we discussed that the degree of a line bundle on the variety is something like a quadratic form. So that's this quadratic sum of this character. So in particular, we know. So in particular, this is independent of which directions are attracting and repelling. Because if I choose different splitting of attracting and repelling directions, what will happen is that some W will change to 1 over W, and so this mu I will change to minus mu I, and so then, but the square will not change. It'll be the same. So the degree is the same, and so then it's so we will require that clear. So this is the actual line bundle. Of course, the actual line bundle will be different, but the degree is going to be the same. And so, so maybe definition. This line bundle S is called attractive if the degree in A of its restriction to any fixed locus, that is equal to degree of A of attracting manifold. And what that class of attracting manifold is, since this is cut out by the bundle, so this is cut out by this is the zero section. Attracting manifold, this is the zero section of the normal bundle. You take the normal bundle to the fixed locus, you take its repelling directions, which we indicate, so this means repelling. So this means that we can continue this equality as the same as degree in A of the theta bundle of this normal bundle to the fixed x over the fixed locus. Yeah. And in general, we computed the degree of the theta bundle in general. So this is like, this is, you compare more from this. From yesterday, this is from last time, this is C1 minus 2 C2 of the. So that makes sense. And then observation. I don't know what the observation. Well, what was the observation I was going to say? Is that so if S is attractive, and of course the degree will not change, so then S tensor L is attractive. For any L that is, well, of degree 0 algebraically, of degree 0. Algebraically equivalent to 0. That's obvious. And in fact, the set of attractive bundle is like a torus or principal homogeneous space over things which have degree 0. Degrees of bundles add upon tensor product. And this is kind of, maybe this is the main point. This is this is a very, very, very important degree of freedom. In fact, we will not construct stable envelopes for one particular. In stable envelopes, you should construct not for one particular attractive bundle, but you should construct for all of them. That's how the theory works. The theory works when works. So this is needed for the theory to work. For variety of reasons, the simplest one I will explain in a minute, but you can ask, what's the degree of freedom? What's the degree of freedom where you might have seen this degree of freedom before? And this degree of freedom before, so this is if you've ever seen an elliptic quantum group. An elliptic quantum group has these funny variables which are called dynamical. Elliptic quantum group. And if you, well, I mean, of course, it's strictly personal. You might find the axiomatic treatment of them. You can find axiomatic treatment very inspiring, but if you've never seen them before, you might wonder, why do you need to introduce them? And so this is the very transparent way to say that you have to introduce them is that they need it for this theory to work, and that's in fact that you can't restrict any particular value that has to move around. And the reason it has to move around is again, it's a very simple reason, is that if I just now let me copy this picture. So if I put mine, something like this. So this is if I want to construct stable envelopes for, so remember the R matrix. What was the R matrix? What was the origin of the R matrix? The R matrix has to do, so I remind you that the R matrix, that was coming from change of attracting directions. Which directions are attracting? Which directions are repelling? In stable envelope. And so this is, so in particular, if we change, so we had previously for one choice of attracting repulsion, we had the attracting manifold here had its class was a product of H bar Wi. This is for one choice. And then for another choice, if we make exact opposite choice, we're going to get the product of the functions of just Wi. And so these have the same degree, but not the same bundle. They differ. So their ratio. So if I take the ratio, if the fact is better, if I better take the like an individual term. So if I take this, just I don't need W, just take 1. Take the ratio. And for beauty, it's better to put H bar here. So this is, what is that? That's not, this is a section of, in fact, Poincare bundle. Remember, we discussed the Poincare bundle last time, so on E cross E. Right? This has degree 0, so it has degree 0 in each piece, but it's like universally non-trivial bundle of degree 0. It's like a universal family, so this has degree 0, but non-trivial. And in fact, kind of universal non-trivial. Where if my E's in H bar, they correspond to kind of. I use, so when I think, so this is maybe a general remark, it's very convenient if you think of E as being a covariant elliptic homology of some group C star, or maybe of a point, maybe U1, then if I have an element for U1, so if I have an element A in the group C star, you think of it as a coordinate. You can think of that as a coordinate. It's like a coordinate. Because you can talk about different things on the elliptic curve in terms of that coordinate. In fact, you can think of that in a way that you think what E is like that's, you know, it's kind of A taking mod powers of K. So this is having coordinates W and H. And so these are, even if I want to serve, in the case of a vector space, if I want to serve the difference between attracting and repelling, I have to include this thing. And so what is in fact the difference? So this is maybe very general. So this I can also write. Like this. So this is like, what is that? This is a section of the theta bundle that corresponds to so remember that I have a linear representation of a torus, corresponding section of corresponding theta bundle. It's just a product of all weights of that linear representation. So this would be of, I'll write it like that, minus H bar. So this is the character of a representation, of a virtual representation. And then if I add a trivial representation to a virtual representation, then nothing's going to change. So this would be the same as saying W minus 1, H bar minus 1. Since a trivial representation does nothing, has a trivial theta bundle. And so this is from now you see it's obviously degree 0 in either factor, because in either factor, if I set the other variable to 1, I get 0. So this is obviously algebraically equivalent to me. And then more generally, so what more general, if V is t equivalent k equals on x, I can take a variable z, which is in some other abstract C star. This star does not act. This does not act on X at all. And then we take theta of, but still it's a bigger group. And so we can take a theta of, we take V minus the trivial representation of the same size. So it's just C times rank V, trivial bundle of the same size, C times rank V. And then times Z minus 1. This is, what's it going to be? Maybe we'll have, this would be a line bundle. On, we take the spectrum on T-current elliptical homology of X cross just another copy of E, which is just where this variable Z lives. And this is of degree 0 in either factor. So this is, okay, this makes sense. And so this is a way, this is kind of a very, a very general way to produce line bundles of degree 0. And so maybe we denote this since it's a very general way. And in fact, I don't know a more general geometric way to produce line bundles of degree 0. So maybe we'll call it U of V Z. And then, so this is a line. So this is an element in peak of elliptic homology T X cross elliptic curve with this new coordinate Z that this has Z. And like I said, it has degree 0 along either factor. Either factor it's degree 0 for the simple reason that if I can specialize, say if I set the variable Z to 1 or take the origin of the elliptic curve, then I'm gonna get the trivial bundle. And so then so this is we're free to twist, so we're free to twist. We have to. We are free to we are well, for one sense we're free, on the other sense we're forced to twist by and why we're forced is that because again for the simple reason that we need to, well, we review this in a second. For the reason I already explained, that if I just change what is attracting and what is repelling, then the bundle itself changes, requires a twist. So that's the explanation. And so maybe exercise. So exercise says, so this proves that if I take this U, well, first of all, if I take any vector bundle Z, I might as well reduce to its determinant. So this would be this. I don't need a general vector bundle. It just takes an uptake line bundle. This is a line bundle. And then second, if I have a, so this I reduce to line bundle, so maybe I take a line bundle, and I have some variables Z1, and a tensor multiply some other variable, same line bundle, some other variable 2. So this is analogous. This is like saying, so this is the same as, so maybe I'll explain this here. Here, this is by definition, that's the same as U of L, and then I add them up. So I take two, instead of taking a one-dimensional torus, I take a two-dimensional torus, and representation, which is one weight plus the other weight. So this, and then this equality that I'm going to write down is equivalent, is like the first equality, but in the second variable. So that would be U of L Z1 Z2. So instead of U of a sum, you instead can multiply. And to prove them all, prove either of them, you can use the theorem of the cube. And it's a useful, something you can, I'm sure you can find in Wikipedia. And the theorem of the cube says that if I have a line bundle on the product of 3 varieties, and if I restrict to point times the product of 2 in 3 different ways, and I get a trivial line bundle, then in fact the whole thing is true. So that's that there. And okay, so this we have. So this gives a, so this is this construction, this use. U is a very general source. Line bundles. 0. But we still need at least one attractive line bundle. And to get that, it's a very useful source of those is if I have to have a polarization. So this would be given by polarization. Of X. So what's a polarization of X? So polarization of X, so by definition, it's a class in K theory and you can, it's enough to, since we're only interested in degrees in A, so we can think as a class in A covariant K theory of X, such that if I take that, such that if I take that class plus the dual of that, then I'm going to get the tension. So this is a way. So if I have a way to select half of the so this is pix. So this is kind of pix. Half of the tension. So this is this is the and since my manifold is symplectic, it is subtangent balanced self-dual. So this, if I picked one and then take the dual, then I should get the whole thing. And so this is, if so, then we can take, then if so, then we can take the theta bundle of that polarization. So this would be, this has the right degree. In general, so this just says that if I take this equality here translates to the fact that the theta bundle of theta 1/2 tensor square equals the theta bundle of Tx. So this is like, so this is for a compact S, this is like canonical bundle of, well, you know, let's not go into that. This is picking a polarization, is picking like a square root of that, of the theta of the tension bundle. It's like a square root of the canonical. So how are we going to get polarization? So most varieties, so a lot of, so if, how do we get symplectic manifolds? So like if X is T star of some manifold M, then you can take the tangent bundle to M, gives a polarization. Or in general, you can go more canonical if I take, so this has a projection phi some M, then you can have two choices, and then you can take pi pullback of the tangent bundle to M. That is a polarization. Or the tangent bundle to the kernel, so or the kernel of pi, of d pi. That's another polarization. So this is like the horizontal. You can check. So if you wanted half of the tangent bundle to cotangent bundle, you can put either the horizontal or the vertical one. So this is like horizontal, and this is like vertical. And so more generally, if X sits maybe it's an open set in the cotangent bundle stack, then the same applies. And so then, so this is the case. This is the case. Open, for example, could be e.g. GIT stable points. In the cotangent bundle to some pre-quotient divided by G. And so then, so this is the case for all. So this covers Markov varieties. So most varieties we're gonna come across in our world will have, in fact, not just have polarization, have a natural polarization. So that's so in other words, concretely, this means that if I take the polarization of X, I want a polarization of X, like for example, in the first case, this I can take I can take to be the tangent bundle to the prequotient. Minus the bundle given by the adjoint representation of G. It's a K-theory cloud, it makes perfect sense. So this adjoint representation of G descends to a bundle on it. So this descends to a bundle on the quotient. Both are G-covariant bundles. And so this to a bundle from the element of KT. All right, so this is. And so then to emphasize the somehow repeat, somehow recall, yeah, to reiterate. And if I'd like, so now, so maybe I'll copy this picture one more time. I apologize for spending so much time at the vicinity of the point where everything is clear somehow. There's no discussion what's the attracting manifold near the fixed point. Near the attracting manifold from where it starts, but I have to set it up all correctly. And it's retrace if I take. So if I have so then so the attracting manifold that is attracting manifold that's restricted to my fixed point f. It's going to be plus minus product of thetas of h bucket i's. Whereas if I want to take the theta of polarization, restrict to f. Well, what I'm going to get? I'm going to get a product that has a section of the form. I take the oval loop overweights. This is where the this is the product of. This is where the products of wi's are positive, and then you take here would be you take a product of those wi's which appear in the restriction of this polarization to point f. So this picks half of them, but we need which half, and so then we take theta. And so the difference between them is easy to see that if I take the theta of the polarization, so maybe this is. So this is take the theta of the polarization, and we take divided by the theta of the normal bundle repelling, another thing. So we're restricted to this pink point f. That is the same as, so it would be, this is a bundle of degree 0 because it sometimes has h, sometimes has this, but it's going to be this universal bundle of what? We take the part of the polarization which is attracting, and you put that variable h part. And then since we already discussed, you might as well replace that by the determinant under the U sign. And so this is the attracting part of the polarization in classical dynamical terms. This is like you take out half of the weights and you look which are attracting. So this is in classical term like the index of a fixed point. So this is in general. So if you have a symplectic manifold, on the symplectic manifold, it's pointless to ask what's the index, because every point has as many attracting directions as has repelling directions. No sense asking for the index on symplectic. But if your symplectic manifold is cotangent to another manifold, you can ask what's the index of that manifold. And then it's a question about the polarization. Which are the attracting directions in the polarization? And so a general formula which this computation shows is that the shift between, if I have a polarization, then in fact, so if S the general, so this is near to fixed locus. And if I want to take a section of so this attracting manifold, stable envelope, where is it going to go to and from? If we want to add and so you can fix either, since there's a map line bundles, you can up to twist, you can fix either the source or the target of that map. So let's just fix the source. So suppose I want to go to theta bundle localization of X. And the source of that map can't be exactly the polarization of the fixed locus. So maybe fixed locus called F. And for this formula, you don't need to assume the fixed locus is isolated fixed points. It just could be polarization of the fixed locus. But then you have to twist it by U of, well, put minus, or I can write it. So what does it mean? I can put minus here or minus there to put inverse. So we put inverse. So this would be U of, you put that index, determinant of the index, and then H bar. And then there's the inverse here. Okay. So this is by the property. So then if I additionally twist, so this is pretty important. It says that even if I fix a polarization, I must introduce that twist, otherwise I'm not going to be in the correct line bundle. This must be there. This shift must be there. So and then we can then additionally, if I have any line bundle inherited from X, I can additionally twist it by anything I want. So I can tensor it with any U of anything, with a product of U of some. You can pick some basis in the car and ZI. Say basis. Pick X. And I can take tensor. So this is, I can tensor the source and target. some reason. Source and target, I can tensor anything I want, but this means that in the direction, so this guy will shift this h bar will be a shift. This h bar will shift to z. Okay. So that's the so this is necessary just already for on that ground. I'm sorry for this lengthy discussion, but it's important to understand. Maybe it's kind of maybe main important point. The main point of this lecture is that if you want something like stable envelopes in elliptic homology, you have to be careful of which line bundle you ask for sections, and the degree of the line bundle is fixed once and for all. But the degree 0 part, that's going to move, and it's going to move around. And if it's moving around, it is the dynamical variable. So this is really dynamic. I mean, people call it dynamic for something else, for some other reasons, but it's in this situation, it's necessary. So this is what. Okay, so now we can somehow now we got started. At least we define. So this defines. So finally, we have defined stuff in the neighborhood of fixed locus. So, try a bad smiley face. So now it remains little to extend it to. We very but we now kind of not extend it to. Now we're gonna extend it to the general, to the whole extend it. Extend. This is really kind of the hard. That's where the hard work is. This. Okay. We're going to extend it in text. And so what will be the induction? How would the induction be organized? So I'll draw the different picture of the same thing. So this is my fixed point. So right, this is going to be a picture which is roughly behind me on this piece of paper. So I'll just draw it somewhat schematically. So I'm going to have kind of a bunch of fixed points, and then maybe I will just need 2 fixed points. Suppose I have just 2 fixed points. This is enough to illustrate. And then manifold is going to go like that. So this would be the x.1 and x.2, and then there will be the subtracting manifold. X.2, and this will be some neighborhood of that. So some neighborhood. of the attracting manifold. And then there will be the attracting manifold phi1. Take out what I've constructed before. So this is the and its neighborhood. And then there will be the rest of X. Okay, so in other words, we define, so we will define the inductor, we will define Xn. This would be the union over I bigger or equal than N, the attracting manifolds of F5. And so in this picture, this would be X2. This would be X1 take out X2. And this would be X take out X1. So this would be, so then, and we will construct, and in every step, we will construct extent stable envelopes inductively. So if I have a variety and I have a subvariety, then there is a long exact sequence in cohomology, namely if I take X, so maybe I'll write in the ordinary cohomology, if I take whatever, some ith cohomology of, let's say let's say we want to, I don't know, let's say we take something like X minus X3, which we don't see in this picture. So X3 is somewhere, we don't see it. So then we can take this just by restriction. This goes to X, the smaller set. So it's going to be X going to go to X minus X2. And then, so this is a long exact sequence cohomology, and this term is the relative cohomology group. So we're going to be HI of X minus X3 modulo X minus X2. So it's long exact sequence. But this is what? This is the Tom space. So this is, we take this is this part. So this is the Tom space of the normal bundle to the attracting manifold of X2. Okay. That clear? So this is there's some parts which I don't even X3 I didn't even write in this picture. It's something we throw out. We throw it out. This attracting manifold is a perfectly nice smooth manifold. It's if we take it modular something which when we remove it, then this would be just the stomp space. Right? And so this would be saying that in elliptic cohomology, what we're going to get is we're going to be this ith principle, some kind of ith cohomology of, sorry, not the ith cohomology, right? There's the cohomology of a Thom space, that's the theta bundle, that's the theta of minus the normal bundle. So this is minus the normal bundle to the attracting manifold. Goes to structure shift. Remember the cohomology group, usually cohomology groups, there are some modules over a ring. So in elliptic cohomology, they become sheaves on the spectrum of elliptic cohomology. So this is where we say the ordinary cohomology, we see that we take the structure sheaf. It's a graded sheaf, graded by degree of cohomology. And then, so this is elliptic T graded cohomology of X minus X3. And then this goes to OI elliptic X minus X2, so forth. But now this incidentally this attracting manifold is obviously the attracting manifold of X2, which is it's just a homotopy invariant to X2 itself, to F2. Not attracting, attracting. Oh, this X2 is the attracting manifold. This is F2. It's just a point. So this is just the same as just F2. And so then we get so this would be saying this object here is just the ith cohomology of, so this is, again, the cohomologies become, all of them become sheaves on the, on some spectrum, some space. Right? So this means particularly all homological gradient, still exists. So we're interested in the zero. In the end, we're interested in the zeros cohomology, but that's for the long exact system, we have to take them all. And so then the normal bundle is just take the normal bundle, or the tangent, whatever, the normal bundle to X over the fixed locus. For this sequence, the fixed locus doesn't have to be a point. Let's just write some component. Some component of 2, 2. It's just it's homotopy of 2. Sum over 2, and we take the repelling part. This is remissive, just repelling. So this is here. And now I claim that this object here, this arrow, this unembedding, and why is it an embedding? Because if we can consider there's a composition, we can restrict back the fixed point. We can take this map. We go to OI of elliptic cohomology of the fixed locus itself. Just restriction. You have a class on the ambient space, you can restrict it to a fixed point. And what is this map? This map here, composite map, This is just multiplication by canonical section of the theta function. This is this object here. This is multiplication. This maybe I'll try and make another attempt to draw this line. This line here. This is this line. This is multiplication. So this is, we're trying to prove that this is an embedding. This is because it's multiplication by the product of the functions of, now I take repelling weights. And the point is, these are all non-trivial. These are all non-trivial A weights. Since these are repelling, they're particularly all non-trivial. All non-zero A weights. And they all non-zero. This object is not a zero divisor. If we take this is some, you know, this is a sheaf of functions that vanish at some point, and this is just structure sheaf, and there is a canonical section, and that canonical section is not a zero divisor. It's just a product of, you know, product of this theta function. So this is not does not divide zero. Or maybe I'll just write non-zero divisor. It's an idiotic word, but I'll write it non-zero divisor. And so this map here is an embedding. And so this means this whole long exact sequence is just splits. Right? It means if this map is embedding, means all the connecting maps are zero. This means this map is zero, and this map is zero. So we have just, so this is. And so in particular, we can look at the zeros. So the zeros, this is, again, we have some complex of sheaf, and now we're going to look at just the zeros term in that complex. So that's how we're going to get, I just drop. So we get theta, and so in principle there should be zero. That zero will just drop. So we're worried about some line bundles, and we don't worry about this line bundles being zeros termed in some complexes. So zero is minus theta bundle of x over 2. Well, goes to O of elliptic x minus x3, and then goes to is there a way to remove that? I apologize. This is Windows. Okay, cool. So so this is this goes to that. Okay. And so now we want to. So now we will take this and tensor with our line bundle S. So the tensor is S. So what we're going to get? We're going to get S restricted to, we'll just write S restricted to x minus S3. Goes to S restricted to x minus x2. Goes to 0. And here goes, well, use whatever it is, S tensor with this, or maybe x restricted to f2 tensor with minus. Let's just write behind normal bundle. And what we would like is we would like to lift sections from here to there. So that was the whole point. So we have the exact. So we want the map from H naught of this to the map from H naught of that. So that's the map we want to know, right? Because we have a class on a smaller piece. We would like to extend it to a larger piece. That makes sense. And to control that, we need, first of all, this question is that's the interpolation problem. And to control that, there's a H naught of this piece. And there's an abstraction that goes to H1 of the same piece. And the whole discussion of these degrees and so forth was that this object here, this is a degree 0 line bundle. Oh, no, I didn't write. Because that's this is on analytic albedo writer, namely the T current homology of well, degree 0, meaning degree 0, so maybe I'll write it like this. Different. Have a line bundle on what? All right, elliptic. Right, elliptic mode of that fixed point. This maps to the elliptic homology of A. This is where that variable h bar lives. This is where h bar lives here. And then, and the fiber with the fiber elliptic homology of A. Point. So this fibration like this, which has degree 0, and they set it up so it has degree 0. It has degree 0 on fibers. Because it has degree 0 in variables A. Okay, 3 attempts to write the word fiber. Let's see if I can manage it. Fibers in this map. Okay. So I have a line bundle which has degree 0 and fibers on this map, of some map, then if I push forward to a point, and in particular I can first push forward to the base, then I should get no cohomology. And so that means this guy here has a potential. This object here has a potential to both vanish. So they should both, this guy's both vanish. Both vanish. If line bundle untrue. So what would be the induction step? So the induction step is if I start with the, I start from somewhere, like if this is like here my stable envelope, which is 0. It's just 0, and so that's there's nothing to define. and then I inductively extend it to larger and larger steps. And so then if I construct, so I want to construct, so how would that go? So we want to step say of f1. This is if we restrict it to x minus x1, this is 0. That's just 0. We constructed it there. So then inductive step, so then the first step, and then we take extend to x minus x2. So then we better get something interesting, right? It's somehow, otherwise if we get the 0 clause, it's not so interesting. And so then we will set it up. We set this up. So this is maybe, we were setting, we were carefully set it up. So that term, that S restricted to F1, tensor, whatever, that is exactly trivial. Is exactly trivial. And so that then there is, so that in that sense, there is some section here, and it is that section, and we're going to pick it up. So that's okay. So then we get. So then we get something on 0. Minus x2. Better be, right? Otherwise, if we constructed, if with so much pain we constructed the 0 clause, that's not so interesting. So we constructed so good. And then we do, and now then we extend it now to x minus x3. And now we need to show that for a general, if we take a general line bundle of degree 0, general S, that thing is non-zero. So we get, need to prove. Need to prove that that this bundle, that S restricted to, sorry, this was F1. 2, tensor whatever, is not trivial in general. Not trivial generically. And so how we're going to see that? This is so this is kind of, there's a very useful lemma if L is ample, then so this is a useful lemma. It's a special case of many other useful lemmas. But so if you have an ample line bundle, then it has, then if I take its weight and restrict it to F1, which is the weight in A, that is not equal to its weight in A restricted to F2. And so in particular, so after, so if I allow a twist by, so after a twist by LZ, this what I'm trying to prove is not will depend, so will really depend on that. On that. And so will. And so will not be true. What's the proof of the lemma? The proof of the lemma is we compute, so we have a trajectory. It goes from one fixed locus to another. And it has, let's close the curve C. So then the degree, so if I pair the degree of line bundle L restricted to C, which must be a positive number if that line bundle is ample, then I can compute, this is computed by localization, is the difference of the weight of L1 minus the weight of L2 divided by the tangent. So just localization. And so that says it's not only that numbers are not equal, in fact, there's an ordering between one is bigger than the other. So that's the proof. And so what we decided, that we decided that we have in this, if we construct, so that says if we construct stable envelope in a family, we allow these dynamical variables. So it means, so this is a construction set. If we allow dynamical variables, then the family that we're trying to prove, of which we only computed that the family of this S restricted to whatever fixed locus to whatever is non-trivial. So if I have a family of line bundles, so in general, if I have a family of line bundles on an abelian variety, it's like a map to the dual abelian variety. If that family is not trivial, that map is not a constant map. Okay? That map might have some dimension. So if that map has dimension D, then the only cohomology that can appear, so this is the only cohomology, so this is like a family, it's like a map to the dual abelian variety, to pick 0 of my elliptic cohomology point. And so the only cohomology that can appear are like it's only cohomology above the dimension of that map, at the dimension of that map, and above the dimension of the map can appear. So this means this is non-constant. And so that says, this means H0 is just 0, and H1 may appear in codimensional. Right? This is some map. It could be a map with one-dimensional target. If it's a map with one-dimensional target, then H1 will appear exactly where that map hits the trivial line bundle. And so that says, so this is, what does it mean? This means elliptic. The conclusion, what does it mean H1 is always 0? H1 is always 0 means elliptic stable envelope is unique. And what does it mean H1 can appear in codimension 1? They may not exist in some subvarieties of codimension 1. This means they may have poles. In the variables that whatever that I and h bar, and these are the variables that I and h bar if along subvarieties dividers. Land on this where that whatever where this object here comes to. We have a line bundle. It depends. So it depends on h bar for this index. This depends. This is kind of through index. From this index term, and it depends on z's through explicitly introduced dependence at some line bundle. It could happen that this line bundle will hit the trivial line bundle in codimension 1. Generically, it's not generically it's not trivial, but it might hit. It can be a divisor where it hits trivial point, and then this means that there will be suppository, in which then I will have pole down. This is why it's important to have them all. And if you fix any given one, not only the theory is inconsistent if you work with just one line bundle, because if you go from, like I said, there's some shift between the source and the targets of this map, and so then you can't really live with just one. But also, if you focus, if for some reason you fixated on some particular value, some particular line bundle, it may be the case that that particular line bundle is a pole. And so that's you have to do something else there. It's right. Maybe maybe since I was hoping that maybe I'll finish on time today, but apparently not. So I'll just remind you that this is what a long time ago we were interested in. We were interested in counting maps through from some Riemann surface C, some maps F to some variety X. And then we studied things. We wanted to study things like sum of all possible degrees, z to the degree, and then somehow count maps of degree t. The reason I'm reminding you of this is that this is the same variable. That is the variable. These are the dynamical variables. The dynamical variables, you think about where they sit in pick X. Well, here they sit in pick X tensor or Z with C star. But then if we further reduce it mod Q to the Z, and we're going to get there. And so this is the reason this is, this might look like an annoyance from this point of view, the need to introduce these variables, but from our original perspective, that was like this is the most important thing that we wanted to study. We wanted to study what was this, what are the properties of the series that, we wanted to know what is the function of Z. So this would be understood in terms of things where Z appears explicitly, Z appears in, so there's some kind of quantum computation. So this is, Z is very kind of quantum here. What did I do with black? I'm not sure. I have to introduce, reintroduce it. So quantum here. Classical. Multi-quantum. That's one point. And the second point is the poles of stable envelopes, they have to do with the poles. And there's this various poles on one side, on both sides. They have they're very directly related. So the fact that there's a stable envelope depends on this variable z, depends on where occasionally hits a pole, has to do with poles of not of this function, but I mean also of this function. So that has to do with poles and singularities, have really correspond to two sides. So the fact that we find something with poles, it's okay, it's good. That's a good thing. Poles are good. If you found something which had if you ever find an analytic function has no singularity, that's somehow. I mean, the theory of entire function is an interesting theory, but it's not the theory that we're going to develop here. We're more interested in things like solutions of rational, solution of regular differential equations, solutions of regular rational difference equations. So anyway, so on this note, that's the proof, and then maybe next time we'll look at some examples and see what it really becomes in real life. All right, that's all what I'm going to say today. How about questions?
Are there typically many more, say for Nakajima varieties, are there more polarizations than the two you listed?
Polarization is a very flexible term. I need two so maybe I should have said, so if I have we only need just one. So because if T is a polarization, this is if and only if, and I can take T and add any bundle I want and subtract its dual is a polarization. So that's if I have one, then you can have infinitely many, but they're not just not going to affect that, because it's if I take the theta bundle, that's going to cancel from the, I'll have the same theta bundle.
Okay.
But I can also take any character I want, like any whatever h to the. So I can put here. I can put like h to 50, h to the 7 here. That'll be also polarization, but it's again in terms of theta bundle, will have the same degree and some shift in. Okay. So different. So maybe but different polarizations means just shift in those dynamical variables. So different polarization. It's like a polarization is like a choosing an origin in some plane or in some vector space, and if you choose a different polarization, choose a different origin. So that's...
Okay, thank you.
Good. Other questions? I'm super happy to receive some questions today. I was pretty scared like there were no questions last time. Is that it? Just one today?
Yeah, I have a question.
Sure.
So you say that the R matrix is what changes between attracting and repelling directions in stable envelopes. Why do you call that in particular an R matrix? Does it satisfy Yang-Baxter's equation?
Yes, exactly. It will satisfy. Well, in this case, it will satisfy the dynamically Yang-Baxter equation.
Okay.
So the R matrices, as we discussed them early in the lecture, they satisfy this sort of Yang-Baxter equation with a spectral parameter. Spectral parameter being covariant variables here, but in this elliptic world, they acquire more variables. They acquire the z's, these dynamical variables, and then the shape of the Yang-Baxter equation gets modified accordingly. So that's gets even more variables. Yes, they satisfy Young restriction. Oh, that's great. So how about more questions? All right, you can always, if you have a question, you can always write to this. There's also like a chat channel, so you can write there. All right, so so the plan for next time is then do examples and do and also look a little bit at what sort of quantum group one gets. So that'll probably occupy. If we talk about a little bit about how big is the quantum group that we're getting. If we look at that will probably occupy a couple of lectures, and hopefully then we will talk about what's the actual connection between this side and that side. All right. Well, but that's all for today, and I'll see you next time.